Good morning, class. We are looking at analytic trigonometry, and here's trigonometric identities. On our text is 7.1, part 2, trigonometric identities. So we already covered trigonometric equations. We're going to go with trigonometric identities, sum and difference formulas, double angle and half angle formulas, and product to sum and sum to product formula briefly. So the objective is to use algebra to simplify trigonometric expressions, establish identities. Again, everybody recalls how to graph sine and cosine functions. Basically, you use 4 arcs. And sine and cosine are ultimately the same with a phase shift of pi over 2. The period is 2 pi, the amplitude is 1. If you happen to have a sine omega x, a cosine omega x, the period changes to 2 pi over omega, and the amplitude changes to absolute value. By the way, this is for a complete cycle. As you know, none of them is one-to-one. The restriction we put on the domain makes it one-to-one in the case of a sine, and for the same token, tangent and cosecant, we put this restriction and we have an inverse. For cosine, we put the restriction of 0 to pi. That works for secant and tangent as well, cotangent as well, and it has an inverse. Now, as I mentioned, for example, tangent follows sine as far as the restriction. What I want you to pay attention to, of course, is that the restriction we put, in this case, from negative pi over 2 to pi over 2, and it includes the endpoints. That's not the case when it comes to tangent. So the restriction is from negative pi over 2 to pi over 2, but the endpoints are not included because they are vertical asymptotes. And then we've learned some of the identities. We are going to look at more identities in this section, but the term identity refers to an equation that is true for all values of the variables involved. These equations establish fundamental relationships that are used to simplify expressions, solve equations, and prove various mathematical properties. So f of x equals g of x. By definition, the two sides of an identity are interchangeable, so we can replace one with the other at any time. An equation that is not an identity is called a conditional equation, meaning it is true at certain points. That's where you solve the equation to find solution for that. Whereas an identity, regardless of the choice of x, it will work. And we remember some fundamental identities starting with the unit circle, x squared plus y squared equals 1. A pair has coordinates x comma y, where x is represented by cosine and y is represented by sine. So the rest of them accordingly follow. All trigonometric functions are periodic functions with the period of 2 pi. When it comes to tangent and cotangent, the period is pi. All of them are odd functions with the exception of cosine, and therefore secant. Cosine of minus x equals cosine of x. And finally, we looked at fundamental identities such as Pythagorean identities. Sine squared plus cosine squared equals 1. Tan squared plus 1 is secant squared. 1 plus cotangent squared is cosecant squared. Quotient identities, tan theta is sine over cosine, cotangent is cosine over sine. Reciprocal identities, cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tangent. These are some of the identities that we have seen, and in order to be able to move on, we should be extremely comfortable with all of it. All right, we want to simplify trigonometric expressions. In part A, we are looking at tan over secant. Many times, the methodology and technique is to go and change everything to sine and cosine. So tangent, as you know, is sine over cosine. Secant is 1 over cosine. Now, you may see that you can cancel those two, or you can say this is a complex fraction. I'm going to multiply by cosine theta over cosine theta. However you do that, okay, it will give you sine theta over 1 or simply sine theta. Either way is fine. Now, in this case, they have mentioned the methodology, but if they didn't, there are a couple of things that I want you to know. Many times we start from one side and get to the other, and we start with the more complicated side. The other technique that is not used as often, but you can use it. Two fractions are equal if their cross product is equal. Okay, so even if they didn't tell you that and you had no idea, because this is the technique you're going to use, you could do that. Let me quickly follow this methodology. We start with the left hand side. Let's say we're going to start with the left hand side. Now, when we do the product, the numerator, we don't touch it. The bottom, as you can see, it's 1 minus cosine squared theta. And 1 minus cosine squared theta can be changed to sine squared theta. So this goes away, and this, you drop the exponent. So we can say this goes away, the exponent goes away, and as you can see, this is the right hand side. Again, let me make sure everybody can read this. Left hand side, right hand side. Okay, so from now on, those are the ones we are going to. If we were to do the cross product to prove that, if we multiply these two, so I'm going to call this method 2. So the product is 1 minus cosine theta 1 plus cosine theta. And we're going to put a question mark because we are proving it. Sine theta times sine theta. As you can see, the left side is 1 minus cosine squared theta. The right side is sine squared theta. They are equal. And that's a proof too. So you could do the cross product. Well, we can do the same thing here. We can do the cross product. Or the technique that was given to us in the previous page, we multiplied both sides by 1 minus cosine theta, and we divided by 1 minus cosine theta. So if we start with one side, okay, if we start, for example, with the left-hand side, then we multiply by the conjugate of this, okay? So please understand this concept of a conjugate, A minus B times A plus B. A plus B is the conjugate. is a squared minus b squared. So the conjugate of this is 1 plus sine theta. Now, needless to say, this blue fraction equals 1, so we can do that. So these two, we just keep him, and the product of these two is 1 minus sine squared, right? According to the product of a minus b, a plus b, and this is cosine squared. Now what happens? We can get rid of the cosine at top and the exponent at the bottom. And as you can see, this is the right-hand side, and it checks. And of course, cross product will do the job. You can try it. I'm going to leave it for you to try it on your own. It's very straightforward, everybody. Okay. All right. We are going to use algebra to simplify the trigonometric expression. Even if they don't give us the hint is LCD, the least common denominator. We are adding two fractions. And the least common denominator would be the product of the two. So in order to add those up, this we will multiply by 1 plus sine. So 1 times 1 plus sine u plus 1 times 1 minus sine u, and the least common denominator is the product of the two. So 1 times 1 plus sine u plus 1 times 1 minus sine u, and LCD is the two. So we can do it in a large, using a large fraction bar, in using one fraction, or you can do two fractions. So please understand, we are raising the first fraction as well as the second fraction, and now their denominator is the least common denominator. As you can see, the product is 1 minus sine squared, 1 minus sine squared u. And the numerator, in this case, is 1 plus sine u. In this case, is 1 minus sine u. So again, the product of these two and these two are the same, 1 minus sine squared. Sine u and negative sine u cancel each other. 1 and 1, they add up to 2. And you remember this is cosine squared. So 2 is over cosine squared u. Cosine is 1 over secant, or secant is 1 over cosine. And so 2 secant squared u. We're going to simplify this by factoring. Again, that's the methodology we are going to use. That's the hint. But even if they don't give us the hint, we should know that. This 1, you can take it to be 1 squared or 1 cubed or to any power, because it makes no difference. So if you go with that, in essence, you're dealing with a squared minus b squared. So the numerator is 1 plus cosine v times 1 minus cosine. And the bottom, notice sine is in common. So if you take the sine v out, you get 1 plus cosine. So factoring is the key. If we cut this into two fractions, this is 1 over sine v minus cosine over sine. And as you know, 1 over sine is cosecant minus cosine over sine is cotangent. The final answer. Again, you have all the questions. We are going over the solutions. Clearly, we are adding two fractions, and the key is to take the LCD. And for the two expressions, the LCD is sine u times cosine u. Which means we're going to multiply this one by cosine, and we're going to multiply this one by sine. So one way is to write this as times cosine over cosine. That means raising it by a factor of cosine over cosine. And over here, times sine over sine. It perhaps makes it easier to follow the next step. The common denominator, or LCD, is sine u cosine u. Now let's put everything in the numerator together. So first, cosine times 1 is cosine u. Then the product of these two is simply sine u cosine u. Plus cotangent and sine, when you multiply, we get cotangent u sine u. Minus cosine u sine u. So simply put, distribute, everybody. Distribute and observe. Clearly, when we write this, we notice sine u cosine u and negative cosine u sine u. Take a look at these two. These two are identical, except one of them is positive, one of them is negative. So in essence, they are opposites. These two cancel each other, right? Sine u times cosine u or cosine u times sine u makes no difference. One is positive, one is negative, they cancel each other. So we write what is left in the numerator. Remember, the denominator repeats. And so we have cosine u plus cotangent u sine u. What is cotangent u? We remember it's cosine u over sine u. When we multiply this by sine u, the sine u cancels out. You get cosine u plus cosine u in the numerator. So everybody, let me show you this. Because it gets multiplied by sine u, changes to cosine u. Therefore, we have two of them in the numerator. 2 cosine u. We can cross out the cosine u. So we get 2 over sine u. In other words, 2 secant u. So the fundamental identities are used to establish new ones. Sine squared v minus 1 over tan v sine v minus tan v. Factoring is the key. Clearly, factoring is the key. And as you can see, this is a squared minus b squared. Sine squared minus 1 squared, right? Sine v plus 1, sine v minus 1. The denominator, tan v is factored out, we end up with sine v minus 1. We can cancel out the common factor of sine v minus 1. And we write what's left. Sine v plus 1 over tan v. We can write this one as a sine v over tan v plus the second part as 1 over tan v. We're going to change, well, this one clearly is cotangent. This one, if we change the tangent to sine over cosine, see what happens. We need to simplify this. If you see the answer is cosine, so be it. If not, I'm going to write it so it becomes clear. Let me rewrite this. This is cosine v. If you write it as sine v over sine v over cosine v, and I'm going to use a different color. This is the main fraction bar. Okay. If you notice, you can say this is times cosine over cosine v, or simply put, let me show you an easier way. I hope you remember this with me. So this was sine v. You can write that as sine v over 1. And you remember, you multiply the extremes. You put them at top. You multiply the means. You put them at the bottom. And clearly, these two cancel each other. You get the cosine. However, you can do that. This is a complex fraction. You can easily simplify that. Elementary algebra. So what I was going over, this is the general format, everybody. AD over BC. I hope you remember that. So these are some of the stuff from algebra. As we come across them, I remind you. We want to establish the identity. We start from one side, we go to the other side. The more complicated side, obviously, is the left-hand side. So we start with the left-hand side. And what we do, we keep the sign. We change the cotangent to cosine over sine and tangent sine over cosine. So here's the left-hand side. Left-hand side. Just remember that LHS, left-hand side. We just change the parentheses cotangent to cosine over sine, tangent sine over cosine. And now all we have to do, look at the parentheses, take a common denominator of sine theta, cosine theta. And I'm going to assume by now we know how to easily add up two fractions. So we want to add these two fractions, everybody. The LCD is sine cosine. So this one becomes cosine times cosine, which is cosine squared. This plus sine times sine or sine squared. So the parentheses changes to this new one by simply taking the LCD sine theta cosine theta. Pythagorean identity, the numerator is 1. So it's 1 over sine theta cosine theta, right? Sine theta from the top and the bottom, they cancel each other. We end up with 1 over cosine theta. 1 over cosine theta, which is secant theta. So I hope it's clear to everybody. It's very straightforward, everybody. We are going to move on. Any questions? All right. We want to establish this identity. As I mentioned, generally speaking, when it comes to the identity that you want to establish, you start with the more complicated side. And sometimes you may not be sure which one is more complicated. You can even do the cross product. By cross product, I mean, if need be, you can put a fraction bar and 1 at the bottom and do the cross product. That will do the job. However, if we start with the left-hand side, cosecant is 1 over sine minus cotangent is cosine over sine. So we are looking at 1 minus cosine theta over sine theta. Now, anytime you have a situation where you 1 plus cosine theta or 1 minus sine theta or 1 plus sine theta is involved, the conjugate of that, okay, can help. You notice the denominator is 1 plus cosine theta. That's what you want to make this one look like that. And this one has a numerator of 1 minus cosine theta. So the key is to multiply by the conjugate. And again, I'm going to write it down. Okay, if you have A minus B class, the conjugate is A plus B, their product is A squared minus B squared. So, of course, you have to multiply by 1. So whatever you put at top, you have to put at the bottom. So we're going to put 1 plus cosine theta at the top and the bottom. This fraction equals 1. So what happens? You write the bottom without changing, but the top is A squared 1 minus B squared cosine squared. This really is handy. And as you know, 1 minus cosine squared, according to Pythagorean identity, is sine squared. Now this goes away. And the exponent goes away. And that's the right-hand side. So you can easily see the answer. All right, we're going to move on. Sine squared minus tan theta over cosine squared minus cotangent theta is tan squared theta. We want to establish the identity. Clearly, the left side is more complicated. So that would be a good choice. We start with the left side. So we start with the left-hand side. And the left-hand side, sine squared and cosine squared, we're not going to change, but tangent, we change it to sine over cosine, and cotangent, we change it to cosine over sine. Generally speaking, when all of them are involved, it's a good practice to bring everything to sine and cosine, and then if need be, take it back to any of those. So let's change this too accordingly. Okay. Now we are dealing with a complex fraction. Complex fraction. To simplify a complex fraction, we multiply by LCD. Look at this one. However many fractions that you have one at top, one at the bottom, and you have total of 2 fractions, and their LCD is sine theta, cosine theta. You multiply everything by sine theta, cosine theta up here and down here. In other words, this and this fraction is equal to 1. So how do we do that? You multiply this one by this piece. So you get sine cubed cosine theta. And you multiply it by this fraction, cosine goes away, and you get negative sine squared. You multiply these two, you get sine theta cosine cubed. And you multiply this two, sine goes away, you get minus cosine squared. So I hope nobody has any problem with complex fractions, multiplications. And now we are ready to move on to the next phase, which is factoring. When you look at the numerator, sine squared is in common. If you take out sine squared, this gives you sine theta cosine theta, this gives you minus 1. The bottom cosine squared is in common. When you take out cosine squared, it gives you sine theta cosine theta minus 1. So take the common factor of sine squared from the top, the common factor of cosine squared from the bottom. As you can see, the two parentheses are identical. You can drop. The result is sine squared over cosine squared. Which is tan squared theta, which is the right-hand side. And we proved the identity. In this case, we want to prove that cotangent squared theta is cosecant theta minus sine theta over sine theta. And again, we like to start with the more complicated side. Clearly, this is more complicated. Although, again, you can set this over 1 and do the cross product. So as we start with the right-hand side, and what we do, we change this one to 1 over sine. We keep this one and this one intact. Only cosecant theta is changed. You're dealing with a complex fraction. The LCD is sine theta. So multiply the top by sine theta and the bottom by sine theta. When you multiply these two, you just get 1 minus sine squared over sine squared. Again, the product of these two sine theta goes in. Now, 1 minus sine squared theta, that is Pythagorean identity, everybody, and it's cosine squared. As you know, cosine over sine is cotangent, therefore it's cotangent squared theta. Which is the left-hand side, and that's the proof. So we are drilling with many, many, many different examples. One minus cosecant theta sine cubed of theta is cosine squared of theta. And again, we want to establish this identity. We start with the more complicated side, which is clearly the left-hand side. So we will change the cosecant theta just this one to 1 over sine theta. So you have 1 minus sine cubed over sine theta. This is sine squared. And 1 minus sine squared is cosine squared theta, which is the right hand side. So it's a very easy proof. One plus tan u over 1 plus cotangent u equals tan u. Again, clearly the left-hand side is more complicated. You start with the left-hand side. And again, I'm going to repeat. You could say it's tan u over 1 and do the cross product, okay? So starting with the left side, since we have tangent and cotangent, we change one of them to the other one. And since we want tangent, let's try to change this to tangent by writing it as 1 over tangent. 1 over tangent. So see what happens, okay? Now we're going to multiply the top and the bottom by tangent because that's the LCD, and the numerator is just simply this times that, okay? So 1 plus tan u times tan u, or tan u times 1 plus tan u makes no difference. The bottom, this is tan of u, these two just 1. Now, whether you have 1 plus tan u or tan u plus 1 makes no difference. They're identical. So they cancel each other. And the final answer is tan u. And obviously, that's the right-hand side, and it checks. We want to establish this identity, and clearly the left-hand side is a more complicated side, which requires adding using LCD, the least common denominator. The least common denominator, everybody. When we do that, the product of the two is the LCD, secant x plus tan x times secant x minus tan x. So the LCD is secant squared minus tan squared. Now 1 times secant x minus tan x plus 1 times secant x plus tan x is the numerator. So we are just taking the LCD common denominator. And again, this one, if you want, I write it here. This piece, everybody, is secant x plus tan x over times secant x minus tan x. When you multiply the two, you get secant squared minus tan squared. Now, let's simplify the numerator. Secant x minus tan x plus secant x plus tan x. So what happens? Negative tan x, positive tan x cancel each other. The numerator has a 2 secant x. Now, one of the identities that we remember, Pythagorean identity is tan squared plus 1 is secant squared. Therefore, secant squared minus tan squared is simply 1. So the denominator is 1. 2 secant x over 1 is 2 secant x, and that's the right-hand side, and that's the proof. So very straightforward, everybody. Let's look at this example. Sine x is minus cosine x tan of negative x. Clearly, the right-hand side is a more complicated side. So we start with the right-hand side. Use a different color. All trigonometric functions are odd functions with the exception of cosine. Okay, so understand that tan of minus x changes to negative tan x. Negative times negative makes it positive. Therefore, positive cosine x times tan x. And tan x will change to sine over cosine. And the final answer is sine x, which is the left-hand side. So very straightforward. sine x over cosine x plus 1 plus cosine x minus 1 over sine x equal to 0. And clearly, it is the left-hand side that is more complicated, and we are going to start with the left-hand side, no questions asked. So we take a common denominator of cosine x plus 1 times sine x. And so this is the common denominator, just multiply. When we combine the two fractions, we get sine x times sine x, or sine squared, plus cosine x minus 1 times cosine x plus 1. So we use the left-hand side. Sine times sine is sine squared, plus cosine x minus 1 times cosine x plus 1. And the denominator is the product of these two. This part is cosine squared x minus 1 is this. And sine squared plus cosine squared 1 is 1. 1 minus 1 is 0. So the numerator is 0. We're not touching the denominator. And 0 over any number is 0, except 0 over 0, which is indeterminate, a different story we discussed in calculus. So the answer is 0, which is the right-hand side, and it checks. So that's very straightforward, everybody. We are moving towards the next question. We want to prove that sine alpha plus cosine beta squared plus cosine beta plus sine alpha times cosine beta minus sine alpha. This is equal to 2 cosine beta times sine alpha plus cosine beta. And clearly, the left-hand side is longer. How about that? The left-hand side is longer. So let's work on that. All right, so let's see what happens on the left-hand side. So we're going to start with the left-hand side, everybody. All right, we're going to square this. Sine squared plus 2 sine cosine A plus cosine squared. Again, reminding you of A plus B squared is A squared plus 2AB plus B squared. And if we happen to have negative sign here, we will have a negative sign here. Therefore, this is sine squared plus 2 sine A cosine alpha cosine beta. It's not A and B. Plus cosine squared beta. These two, okay? A plus B times A minus B is A squared minus B squared. So the product of these two is cosine squared beta minus sine squared beta. So this uses A plus B, A minus B. So this is what we have. The left-hand side And you don't have to write the left-hand side. You don't have to write this. The left-hand side is equal to this. Again, raise this to the power of 2, multiply this 2. This is what we get. And all we have to do now is simplify. So notice sine squared and negative sine squared are there. They cancel each other. So we have this. Plus 2 of those. So we factor out number 2. We factor out cosine beta. 2 cosine beta. When we take out 2 cosine beta, we are left with sine alpha here plus cosine beta here. And that is the right-hand side. This expression, and we are done. We're going to move on. We want to simplify this expression. And as I mentioned, most of the time we go with sine and cosine. So that is the hint. But even without that, we're going to change the cotangent to cosine over sine. And cosecant, we're going to write it as 1 over sine. By the way, this is whatever the variable. This is x. Now, you can multiply the top and the bottom by sine x, or you notice both of them are the denominators. You can drop them, and the final answer is cosine x, and that's the simplified version. We want to show that cosine theta over 1 plus sine theta equals 1 minus sine theta over cosine theta. And we've had similar questions before. In fact, we had cosine theta over 1 minus sine theta equals 1 plus sine theta over cosine theta. So they interchange those two. And that's why we use the same technique, okay, which is multiply by the conjugate of one of them. So you can start with one side. Obviously, we at this point really doesn't matter which one you start with, okay? So if we start with the left-hand side and we multiply by 1 minus sine theta over 1 minus sine theta, the numerator is just the product of the two. The denominator, 1 plus sine theta and 1 minus sine theta, their product is 1 minus sine squared theta. And as you know, 1 minus sine squared is cosine squared. I can drop this one and the exponent of this one, and that is the right-hand side, and it checks. All right. We want to prove tan V plus cotangent V over secant V cosecant V equals to 1. And we start with the more complicated side, obviously the left-hand side. And the technique is most of the time when you have tangent, cotangent, secant, cosecant, if you go with sine and cosine, you can't go wrong. So tangent is sine over cosine, cotangent is cosine over sine, secant is 1 over cosine, cosecant is 1 over sine. So we need to know all those identities, and we need to know them pretty good. Complex fraction. Again, reminding you, complex. The technique is to multiply by LCD. You have 1, 2, 3, 4 fractions. If you have even 10 fractions, the LCD for all of those is simply sine times cosine. So we multiply the top. This is the main fraction bar. Let me. Main fraction bar. So multiply the top by sine cosine, means sine V cosine V, and do the same thing for the bottom. This fraction is equal to 1, so it's acceptable. So if you multiply this by this, let me use this color. When you multiply it by this, cosine goes away. You get sine squared. When you multiply it by this one, sine goes away. You get plus cosine squared. When we multiply the bottom by sine V cosine V, everything goes away. You get simply 1. And as you know, sine squared plus cosine squared equals 1. That's one of those Pythagorean identities. So this is the right-hand side, and we are done. We proved that. We want to prove that ln of secant theta plus tan theta plus ln of secant theta minus tan theta equal to 0. Needless to say, the left-hand side is the more complicated side. So we're going to start with the left-hand side. And I'm going to remind you ln of x times y is ln x plus ln y. I hope you remember the properties of logs. So what I'm going to do, I'm moving this way. So the left-hand side is the ln of the product of these two arguments according to this formula. So ln of secant x plus tan x, x or theta, I keep, sometimes changing them. It really makes no difference. Let's say this is x. Everybody, let's change. It really doesn't matter. So what happens is that when you do the product, you end up with what? Secant squared minus tan squared, right? Secant squared minus tan squared. So ln of secant squared minus tan squared. And I remind you of one of those Pythagorean identities which says tan squared plus 1 equals secant squared. We had looked at this before. So if we move this to the other side, secant squared minus tan squared becomes 1. Let me write that. if I move this one to the other side, and ln of 1, we should know equals 0. And that's the proof. Okay, everybody? Very straightforward. I hope everybody's okay with that. Any questions? Again, a lot of stuff come to work here. Information from algebra, information about logarithmic properties, you name it. Okay, so that is extremely important to remember. Everything that we've learned in the past, it's really a must. Okay, it's a must. So I hope everybody's okay with that. We want to establish this identity: sine squared of negative theta minus cosine squared of negative theta over sine of negative theta minus cosine of negative theta equals cosine theta minus sine theta. And clearly we start with the left-hand side, which is the more complicated side. So left-hand side. So first and foremost, I want to make sure we understand this means sine of minus theta to the second power. Let me just write one of them so you see what happens. The meaning of this is sine of negative theta to the second power. So I want to discuss that and we can figure out the rest of it. And sine of negative theta equals minus sine theta. Remember, all trigonometric functions are odd functions with the exception of cosine. So what you have here is cosine of minus theta squared. So this one, sine of minus theta becomes minus sine theta squared minus cosine of minus theta and cosine of theta are the same. This is cosine of theta squared. The bottom, minus sine theta minus this is the same. Cosine of theta and negative theta are the same because it's an even function. So this is how you make the change. And all we have to do, simplify. So when you square this, becomes sine squared theta. When you square this, it becomes cosine squared theta. So simply put, this negative, because it gets squared up, makes no difference. So sine squared minus cosine squared. And sine squared minus cosine squared, since we want to simplify, rather than any other method, we just use a squared minus b squared, and we write sine minus cosine and sine plus cosine for the top. So we are looking at a squared minus b squared class. A squared minus b squared. And we know a squared minus b squared is a minus b, a plus b. So the numerator is sine theta minus cosine theta times sine theta plus cosine theta. And the denominator, just take the negative sign out. Negative sign out. So simply put, factoring is the key. So we have sine theta minus cosine theta in the numerator. We have negative 1 in the denominator. So basically everything changes. The numerator, this becomes minus sine theta, and minus cosine theta becomes plus cosine theta. You can write it in this fashion, but we rather write it in the fashion that is given as a right-hand side, and that establishes the identity, and that's a proof, everybody. So that's a proof of this identity.